Yep.
Okay, good. So then, as introduced by Romain, the idea today is to have a presentation on microscopy. I'll try to mix some examples, some basics, and some physics. And I'm not speaking on behalf of Thermo Fisher. I try to make it completely focus on applications. There will, of course, be examples on the technologies we have and also some other competitors they have, but this is out of the story here. So then, first, just what is a TEM? I don't know if many of you seen a TEM or use a TEM. This is how a TEM looks nowadays. It looks like a big fridge. So most of the systems are enclosed today. And typical size we have here, a scale bar, would be about 4 meters in height. So it's a quite tall instrument. Can be quite expensive. For a system, we'll be talking, a simple system would be €500,000. A complete system could land.
Sorry, Daniel, are you sharing the screen? Because I cannot see the screen right now.
Just let me make sure. Okay, let me see. Okay, Can you see it now?
Not yet. Do you guys see the screen? I cannot see it here.
No. So now I allowed some GB physics to enter. Maybe if you retry.
Let me try once more. What about now?
Yes, coming.
Yeah, perfect.
Oh, okay, perfect. Now you can pull full screen, I guess.
Okay, very good. Is it working?
Yes.
Okay, very good. Okay, so then this was the TM I was showing you. This is how it looks now nowadays. It's a very recent model. As I said, looks like a big fridge. It has enclosure for stability. And for you to have an idea in terms of size, we're talking the range of 4 meters high. So it's a pretty big instrument. And what is inside of that box, it's pretty similar in all electron microscopes. So if you see different brands and different models, it's essentially the same. I'll go more into details there, but essentially we have one electron gun shooting electrons down a column that is in vacuum condition. And then these electrons, they go through a sample, and we work with the transmitted signal. So that's transmission electron microscope. So that's the basic idea. There are some models that are smaller. Basically, it depends on how much you have on your optics, how many elements you have to fine shape your probe. And then these are the microscopes from Thermo Fisher. But then I also brought the image from other microscopes, so I have an idea how different the microscope can look like. So here's a huge microscope from Hitachi. It's not so common nowadays, but then this microscope would go to mega electron volts. So, and then just to put a scale bar is a bit difficult, but this is the size of the operator next to the microscope. So it's a huge column. You also have miniature TMs. It's pretty recent, but then the size of, well, you can scale to the monitor here. There are some TM microscopes that look much closer to a synchrotron facility or a beam line, more, well, open experiments and more flexible in terms of what you can do, and sometimes more complicated. And the most usual, when you think of a TM, I think that this is the most common image. It's a microscope that you sit next to it. You have the binoculars to observe a fluorescent screen, and then this is the environment that's the most famous one, even though nowadays most of the TMs are operated remotely. Then the concept around TM, so from its inception with Ruska, and no, it was in the early 30s, it's pretty similar to what we had in the commercial implementation by Philips and what we have today. So the idea behind the transmission electron microscope hasn't changed much, and is essentially described here with this diagram. So it starts from top to bottom. We think that we want to extract electrons from a tip, from a source, and then we want to accelerate these electrons down a column. And we're going to use electromagnetic lenses to shape the probe that is going to land in the sample. There are some techniques that we are going to use a parallel illumination. There are some techniques that we want to have a convergent illumination to focus a small probe. And for TM, what we're going to analyze is the signal that's coming through the sample, the electrons that are passing through, and we're going to learn, well, some physical insights to generate the image and then use the characterization aspect. So that's the core concept. And one important thing that I'm going to mention here, and probably I'm not going to talk much about it later on, is that all this structure, the column and the liner, it's under vacuum. Because you have electrons are pretty reactive, and if you have gas inside this column, you're going to have multiple scattering, and you're going to mess your beam formation and signal overall. Then this is, in a nutshell, what a TN microscope is. And here, just the most traditional TM result. So if you've seen TM results before, probably this is what you've seen if you've seen the most common TM applications. So there are imaging techniques that can reach high resolution. So this is one example of a TM image. And in TM image, we have a parallel illumination. So the beam lands to the sample in a parallel way, and we form a shadow image onto a camera. So the idea is one shot, one kill. You have one image that's based the shadow of the object over the camera. Then you have scanning TM imaging modes that you form a small focus beam, and then you raster over the sample and collect signal point by point. And this is very similar to the concept of the old televisions with the CRT technology. Then those are the imaging approaches with TM. They're the most common ones. And one big advantage of the TM is that when you land high energy electrons to the sample, you have interactions going on. And one of the most important ones is that you have electronic transitions that are typical for the chemical elements that you have in the sample. So basically you have ionization events and electron decay that are going to emit X-rays with certain energies. They're typical for those transitions. And if you capture those X-rays and sort them in energy, you have the EDX spectroscopy. And then by checking the energy of those X-rays, you can get the chemical composition. And if you count those X-rays, you can compare the ratio of these different elements. So you can get a quantitative analysis of the elements you have in your sample. And then, of course, if you make a small probe and you do this point by point, you can do chemical mapping. And then you can look at a high resolution. It goes down to atomic resolution nowadays. What are the chemical elements present at different sites of the sample? So for instance, here, it's a zirconium oxide particle doped with erbium, and then we can localize where these erbium atoms are segregated. So these two slides, the high resolution imaging and the EDX capability, I would say that is 80% of what's done with TM today, and it's the famous, but then you can more with it. So one strong TM is that you alternate imaging and I'll go into more with a TM. So one of the strong features on TM is that you can alternate in between imaging and diffraction modes, and I'll go a bit into more detail later on. And with electron diffraction, you can study the crystallography of your sample. So you can recover structural information directly from the diffraction result. You can do tomography. So, and tomography experiments, you're essentially tilting the sample and acquiring multiple images or multiple chemical maps. And then from this projected image, you can reconstruct the 3D shapes. Then you can reconstruct 3D morphology and even chemical segregation in 3 dimensions. You can also do in situ experiments. So for instance, you can heat up the sample and see live what happens when you change the temperature around your particles or around your sample overall. Or you can have controlled environment. Here is one example that you have a mixture of oxygen and nitrogen, and you change the temperature. And these studies are pretty famous for catalysts, so that you can study how the materials they behave when you change the atmosphere around them. Then there are some other techniques like measurement of mechanical properties, such, well, strain states in materials. It's pretty common for semiconductors. Or you can study magnetism, checking the size of magnetic domains and how they're present in the native state in your samples. Well, those are a bit more advanced. There are many other possibilities, and this is TM is a good laboratory tool in terms of allowing many different kind of experiments with scattering, and this is the impression that I want to leave today. But this is not what most of the people do when they are using the TM. Then a brush on the theory. I think that this is the starting point if you want to understand what is possible to do with a TM, is to understand the scattering events that you have when you have a high energy electron beam going through a thin specimen. So the first that you expect to have is that many electrons are not going to scatter when going through the sample. There's a high probability for a thin sample that electrons are going through without any loss of energy or any deviation. Then there will be some elastic scattering, and for instance, diffraction happens here, and also high angle scattering, Rutherford scattering is going to happen as electrons they go through the sample, and many events related to energy loss. So the electrons, they will go through the sample and they are going to have interaction with the sample, and they are going to lose energy in many ways, and this will result in different signals that you can use to study the sample. And there will be generation of X-rays, so Bremsstrahlung X-rays, so breaking signal from X-rays. Also the characteristic X-rays that I described before related to electronic transitions after you ionize the atoms in the sample. You're going to have the generation of visible light, ejections of sample electrons. You're going to have backscattered Auger, and well, it's really a jungle. So when you put high energy electrons through a thin sample, you're going to have many effects like this. And when I mention high KV electrons, here typically we're talking in the range of 300 kV electrons, so 300,000 electron volts in energy. And this is on the higher side of the electron energy, and down to 30 kV. So 30 to 300 kV is the typical range that we're talking on a TM machine. And then the idea is that we're shining our electrons in the sample, and we're going to collect these different signals to understand better what is there to study. So for instance, the TM imaging that I mentioned before, we're basically capturing the direct beam and checking what's the shadowing effect. So regions of the sample that do not scatter much, they're going to appear brighter than the regions that scattered electrons more strongly. And for this reason, we use a camera there at the bottom of the microscope to capture those electrons and to have this representation of the direct beam. We can also use the collection of the bright field or the direct beam in STEM mode. And with this, we're going to have similar information. It's just collected in a different way. And we can also collect different scattering ranges. And this is the core of STEM microscopy, that by collecting different annular ranges for the scattering, you're going to have different contrasts. So for instance here, if you collect what's called the dark field, that's an intermediary scattering range where diffraction effects dominate, we're going to see shining bright in the sample the regions that are heavily diffracting. And if we capture higher angles, so this high angle annular dark field region, we're going to have the Rutherford scattering dominating, and then here the contrast is going to be essentially related to the atomic weight of the sample to the square. So then with the different scattering ranges, we can learn different information about the sample, and this is how we explore these different signals to generate images. And then for capturing electrons in different annular ranges, we use segmented detectors with different annular ranges, and also we use the optics to change the projection of the electrons as they go through the sample. Then, as I mentioned before, we have X-rays being generated. When you put high energy electrons through a sample, you're going to have ionization interactions, and this is going to generate X-rays in the decay. And then the energy of those X-rays is going to tell you about the transition that is there. So if you check, there is a comprehensive database mapping all the existing transitions that are expected, and what's the typical energy from them. And with this, we can identify the chemical species as we go. The Bremsstrahlung is a background radiation, so this would be this decaying background we see in the image here, and this does not contain much information, but is one side effect on this electron generation, or X-ray generation, sorry. And to capture those X-rays, what we typically do is that we surround the sample inside the microscope with detectors. And here's one example of well, is a depiction of the sample holder with a sample inside. We typically use 3mm grids, and the space that the sample is located in between the pole pieces of the objective lens is about 5mm. So it's a narrow space, and we managed to put around many detectors to capture as much as we can the X-ray signal to build those spectra, and also to allow for mapping. Then another important aspect of the analysis of in the TM is to check the inelastic signal, because from it we can learn how much events that led to energy loss happened. So the technique is called electron energy loss spectroscopy, or ELS. And on the right here, you have one example of a ELS spectrum, and you can see you have a lot of electrons. Most of the electrons, they are at zero, so it's called the zero loss peak. So for a thin sample, this is expected that most of the electrons are going through without losing energy. And then we start to see many peaks related to different losses here. So for the low energy losses, we have mostly electron-electron interactions, and those are going to reveal effects that are related to the optical properties, to the electronic properties of the material, for instance, plasmon losses. And then as you start going up in energy, you start to have the energies related to ionization events, the same ones that generate the X-rays that we analyze in EDS spectroscopy. You have the same energy loss encoded in the electrons that went through the sample. So basically you have equivalent information, either collecting the X-rays that are generated, or with this decaying after the ionization event, or collecting the electrons that went through the sample, lost the energy to excite this transition, and then can be captured and analyzed. Then, of course, the idea is that if you analyze the energy loss, you can have much finer information on the inelastic events, and then you can learn about the chemical composition with the core losses. You can get the fine structure, so information related to the oxidation states that you have in the sample with the fine structure of the peaks, and you can go to the limit of information that is much finer. And nowadays, we're starting to get resolution enough to understand phonons inside the TM. Of course, the energy resolution is not there yet to compare with X-ray techniques, but then the compromise is that the spatial resolution is much higher, as you can map locally these effects. So this example here is the measurement of phonon distribution at the sides and the edges of a magnesium oxide cube, and then it's possible to distinguish the phonon modes that you have at the surface and at the corners here. And this is a very recent possibility. It has been, the first report such kind is from 2015, and this technology is just now available as a more commercial aspect. So still, there is much in terms of evolution of ELS spectroscopy and TM microscopy overall. And then how does it work is that we have at the bottom one energy loss spectrometer. So it's basically one device that is going to capture the electrons after they go through the sample, and is going to sort the electrons in terms of the energy. And then you can have this function. You count electrons by the energy that they lose, and you can retrieve this kind of information. Then there are many other signals that they are not widely used on the TM, and such as the secondary electrons, the backscattered, and the light generation when cathodoluminescence that you have there. There are techniques that can explore this, but they're typically done on different microscopes, and the main reason is space. So to collect light or backscattered electrons, you need to have a more efficient collection around the sample, and in the TM, well, it's optimized in a way that putting an extra detector there would harm the resolution. So then the idea is that this is just not explored because of, well, space constraints. So typically,
Daniel, so regarding space constraints, so the samples, usually do you have to make a special treatment? Okay, there must be a limit in the size of the samples, but you have, I mean, if you have an amorphous sample, is it really much worse than using like a crystalline kind of structure? I know that the light, the things that will be emitted will be very different, but how constrained are you from in the samples structure?
I have some slides later on more related to sample preparation. I'll go there in more detail, but just to give you a quick flavor, we use 3mm grids. So in size, we have 3mm that is fitting the sample holder. And then the sample needs to be thin enough so the electrons can get through. So this depends on the elements that you have. So if you have, for instance, tungsten-based samples, you can expect that you need to get much thinner than if you have, I don't know, magnesium oxide. So depending on the composition and also on the electron energy. So you need to thin down the samples so they can be useful.
Oh, I see.
But then I'm going to give a bit more detail on the practical aspects for TM later on. Can I elaborate a bit more and then I comment?
Yeah, perfect. Thank you.
Good. So that was the first part, just to give you a brush on what is TM, what are the basic ideas behind. I hope that was not too basic or too boring. Now I'm going to enter a bit more in details on what are the imaging approaches and what happens when the electrons, they go through the sample, and well, what can be expected in terms of optics there. So I'll start here first with the TN mode. That's the one that is the most traditional, or used to be the leading one. And the idea here, in this depiction of the electron on microscope, you have the gun at the top, you're emitting electrons, and you're going through this CL region, that's the condenser lens setup, and then you're going to get to the sample, that's the blue line here. And in TN mode, we want to land a parallel beam over the sample. So remember, we want to make a shadow of the sample against our camera. And then the magic happened here where there is the exclamation mark, and it's a bit more complicated to put on this diagram. So then let's zoom in to see what happens after the electrons get through the sample. So these are the two diagrams on the main imaging modes that we have for generating images, that's the left, and the diffraction patterns on the right. So I'll try to cut the complexity here. If you look at the top, you have the specimen, and the electrons, they go through the specimen, they're going to scatter. And then the objective lens is going to pick those electrons and put them back. And on the back focal plane of the objective lens, you're going to have the diffraction pattern. So that's the point that a parallel beam would result on a single conversion point of the objective lens. And that's the diffraction plane. And then if you continue the propagation, just below the back focal plane, you're going to have the first plane that will give you an image back. So that's the first intermediate plane. And those are the two important planes. You have one plane that you have diffraction, and then below it, you have an imaging plane. And then the rest of the optics below the sample, they're just going to help you selecting what plane you want to throw to your camera. So then you have a lot of lenses. You have the intermediate lenses, you have the projection system, and the only thing that they are going to do is that they're going to pick either the back focal plane of the objective lens or the first intermediate plane and project this to your camera level. And this is the distinction in between you projecting one image or one diffraction pattern. It's a change just in your intermediate and project lens. And this is how a diffraction pattern looks like. This is the first diffraction pattern that I acquired. It was there in the synchrotron lab, and it was recorded on a film. So then that's why there is an invert contrast. So if you acquire this in a camera, that's the common practice today, it looks inverted. So this is how a diffraction pattern of a polycrystalline sample looks like. So you have the rings that the distance from the center, they represent the scattering angles or the allowed diffraction angles. So where you have constructive diffraction. And if you have a monocrystal, you're going to have not this ring-like pattern, you're going to have defined spots that are related to scattering in two directions. So basically, what you have in polycrystalline, you have defined interplanar spaces that are going to generate your diffracted components. But then you're going to have a rotational average because you have many crystals diffracting, well, to any direction with that particular scattering angle. And then for a monocrystal, all the atoms, they are in the same relative orientation, and you have this nice spot pattern. And if you push the button and go back to the imaging mode, so basically what you're telling the microscope is, now I want to look on the first intermediate plane. You'll be looking not at the diffraction, you'll be looking at the real image. So this is the region of the sample with multiple particles that generate that diffraction pattern with the rings. Or for the crystal, this is the region of the crystal that generates that nice spot pattern.
Excuse me. How can be a distinction between a polycrystalline and monocrystalline in this pattern of the diffraction pattern? How can be distinguished?
Sure. So if you look at a monocrystalline pattern, you can check for the distances here. So you take the central spot, the brightest one that you can see very close to the center. You're going to see that you have here, it looks like a cubic material, and you have very defined spacings. You have the multiples there. So this will be probably the 100 and so on, so forth. And you have this on a single slab of material scattering. Now imagine that you have multiple of those monocrystals just rotated with respect to each other and in different orientations. So then if you have enough of those crystals, you're going to have this ring-like pattern. So the way that you distinguish in between a monocrystal and a polycrystalline material, of course, within the area that you're illuminating, is if you have a spot pattern that is related to with spaces and angles of a certain viewing of a crystal, this is going to indicate a single crystalline domain. And then if you start to see points that are not directly correlated, so for instance, there are not linear combinations of two other points, then you start guessing that you have more than one crystalline domain. And of course, if you start adding up a lot of them, you're going to fill in the circle, and then you only have the distances. Does it make sense to you?
It's clear now. Thank you.
Yeah, it's a bit of an abstract concept, but imagine here, if we take any of those small particles and we take the diffraction pattern of those individual particles, they are going to look like monocrystals. They are going to have certain scattering angles depending on the orientation of the sample. Some crystalline planes will be in diffraction condition, and then each one of the particles is going to have one pattern like that. But then when you add all those patterns together, you're going to get an averaging effect. I hope that this make it a bit more clear. Then the next thing is, if you grasp this concept, then you can understand the next step is on how can we get atomic resolution. So what happens when you have atomic resolution? Imagine that you have a single crystal, like I showed before, and you're going to have a central spot that is typically denoted as G0, and you're going to have diffracted components, and they are always symmetric. And then you have GA, B, and C. They are basically here allowed reflections that are constructive to the diffraction effect. And then this is on the diffraction pattern. And then when you go and further propagate those components, they are going to reconstruct the image in terms of frequencies. So another way of thinking this is that the TM is basically, or the objective lens is essentially a machine that is going to do a Fourier transform. So you have the sample that's your real space. What you see in the diffraction pattern is going to be related to the spatial frequencies that will be allowed because of constructive diffraction effects. And if you continue propagating, those components are going to recombine, and they're going to generate an interference pattern. So if you allow all these diffracted beams to be propagated and recombine on your image plane, what you get is an image like this in the end. So this is one high-resolution TM image of a cerium oxide. And then you can see here, well, what many people would immediately say, oh, hey, those are atoms. And then I'm just going to skip a few slides to tell you that those are not necessarily atoms. This is just the interference of the diffracted components, that they interfere in a way that it looks like a spot pattern that can be related to atoms. So the spacings, they will be directly related to the space of the crystallographic planes, but not necessarily here you're going to have one atom per bright spot. But the idea behind high-resolution TM is that you're taking the diffracted components that come out of your sample after you pass with the high-energy electron beam, and the objective lens is going to bring all these components together, and they're going to make them interfere. So in this aspect, high-resolution TM is an interference image technique. Then the question, if we're really seeing the atoms, I think that the nicest way to think about it is let's think on how the electrons propagate through the sample and how the image is formed, and then you can have an idea if those can be real atoms or not. So if you think backwards, what's happening when the electrons, they go through the sample? Let's first define a sample. To define a sample, let's put a crystalline model that we have different atomic types in different positions, and they may be vibrating. So depending on the temperature, they're going to have delocalized potentials, but then this is another story. Then what we're going to have is that depending on the orientation of this crystal in the space, so the angle that we're seeing, and we can model what would be the potential of this crystal. So basically, you think of a three-dimensional potential structure that is going to be how your sample is going to interact with the electrons passing through. So here, if you represent any given sample as a crystal model, and knowing the atoms, knowing their position, their orientation, and also their atomic scattering factors, you can think this as a big 3D potential that your electron wave is going to interact with. And then the best or the practical way to calculate what's coming after the sample is what we call the multi-slice. And basically, it's a very complicated calculation if you want to interact an electron wave with a 3D potential that's complex in terms of having multiple atoms and multiple sites. There will be a lot of divergence. So what is done in practice is that we think of slicing the material. So basically, the 3D sample, or this nanocrystal that I depicted here, imagine slicing it in very thin potential slices. And what is done is that we input an electron wave, and then basically what we need to know is the energy of the electrons and the conversions that we have, that in this case will be very close to parallel. And then we're going to have the interaction with one slice, with the top part of the sample. And then we're going to have here what is denoted as Qn xy times the potential function of the sample xy. So basically, we're going to calculate what is the electron wave looking like after you go through the first slide, and then you propagate until the next slide. So basically, this is a way to consider your sample, to think of your sample of a succession of 2D slices instead of a 3D. And this is just an artifact that you use to calculate it in an easier way. So here, when you think of this way, it's easier to understand that as the electron wave goes through the sample, the phase of the electron wave function is going to be delayed as it goes through the atomic centers. And basically what you're going to have is that there will be certain points that after interacting with a number of atoms, there will be a wraparound. So instead of getting brighter, it's going to get dark because you have a phase delay. So this already gives a hint that even without considering the optics, as the wave goes through the sample, an atom may appear dark or appear bright depending on how thick the sample locally.
Daniel, excuse me, I did not understand very well how you defined your slices. are these atomic layers or molecule layers, and then you propagate until the next layer?
Yeah. Here, it's something that what we do in practice is that we define a layer that is thin enough that is going to generate locally an interaction that is not going to give you 2 pi of a phase shift. So that means that it's important that in each of the interactions, the potential is weak enough that it's not going to give you one wraparound of the potential. And then this layer thickness depends on the material. If you're calculating organic material, for instance, or light elements, you can have even a nanometer layer on your calculations. It's going to work. And if you have gold, for instance, 1 atom may be sufficient to do this wraparound. So it's not a good approximation. So it depends on the.
Okay. It's not connected to the physical position of the molecules, the atoms.
Yeah, what you need to retain is the physical structure, the 3D structure, but then you generate arbitrary slices to simplify the the calculation of the wave propagation.
Okay, thank you.
Okay, so then this is how the electron wave looks after exiting the crystal, but of course, it is not the image you get at the end. What you're going to have is how your microscope is going to transmit this information. And then the idea here is what we call the contrast transfer function. That is essentially how the microscope takes these electrons and project them to the camera. So ideally, we would expect to have a perfect transfer. So for all the different frequencies, we expect to have it as +1. So basically, all the frequencies are transferred and without loss of information. But then what happens in practice is that we have a physical cutoff. So there is a physical dimension of the microscope, so not all the scattering angles can be collected. So then there is a cutoff that is called the aperture function, that typically is not the limiting one. Then there is a coherence function that is going to be a dampening of this transfer function. So that essentially means that for very high spatial frequencies or for very small spacings, the coherence of the electrons or the optics is not going to allow you to reconstruct such a high frequency. So for instance, this comes from the energy spread of your electron source. Ideally, we want all the electrons being at 300 keV after acceleration, but there is a deviation, so there is a delta there. And also the emission size is not a point-like, there is a physical size of emission, and all of this impacts in the coherence of the electron wave and how far you can get with the spatial frequency transmission. And then the last, you have this oscillation function here that's related to the aberrations. And this is going to be, in a first approximation, related to the defocus that you use for your lens and the spherical aberration. So this is essentially the lenses are looking at a certain plane, but then electrons being at a different position in the X and Y, it's going to transfer in a different way. So basically the lens is not perfect. It's going to have defocus astigmatism effects that if you expand this into a series, you're going to have an overview of the aberration. So this transfer function is what you're going to apply to the electron wave that is going to come out of the sample. So both of these effects will lead to inversions in the contrast. So the main message here is that what you see in high resolution TM is not necessarily white spots for white atoms. There is the transfer of the electrons, so the electron wave going through the sample that may have reversals, and also your lenses can do reversals in the transfer function. Then next here, to get a bit lighter on the optics, is just a view on how these aberrations they change the game, and a bit on how the microscopes evolved recently. So here's a video from Forschungszentrum Jülich. It's one of the leading centers in microscopy, showing one scheme on what happens when you do traditional TM microscopy. So here's the scheme of the microscope, and if you see in the tail, there is a sample, there's the scattering rays, and then these scattering rays are going to be modulated with the objective lens and with all the projection. And what you have in the end is an image that will retain the frequencies of the sample, but not necessarily the position of the atoms as bright spots. And this is mainly related to the aberrations for very thin samples. And then the development was to improve that, is to add a corrector to correct for the higher order aberrations of the lenses. So the most important one is the spherical aberration. And the idea is that you use a series of multipoles to counter this spherical aberration. And here, without going into too much detail, the spherical aberration is a tricky one to correct in regular light optics. What you do is that you use a divergent lens to do that. But then when you're talking about electron microscope, you cannot do a divergent lens individually. It's just not allowed by the, well, electromagnetic lens design. And the way to do that is to break the symmetry using multipoles. And this was a breakthrough that was somewhat recent. The first implementation of it was the end of 90s. The first commercial system was in beginning of 2005, if I'm not mistaken. And those four gentlemen here, they're the leading guys in this field, the guys that developed, they calculated the optics, that implemented the hardware and they tested it. And there's even a bit of a joke that this is not only, the only reason that they did not get the Nobel Prize is that there are 4 people involved with it. And the guys, they just cannot agree, well, on the top 3 there in this area. But then the aberration correction in TM led it to another level in terms of resolution and possibilities. So, and this is where we are today in TM capability. So this is the most advanced.
Daniel?
Sure.
Excuse me. So this is a question from the beginning. You showed microscopes of very different size, from 1 meter to another one of 10 to 15 meters. So this was my question is, what do you gain? Why do you need such a large size? Is it for correction of aberration? Do you get some faster electrons, or why do you want to grow in size your microscope?
Okay, so historically, the size was, okay, when you think of that big Hitachi that I showed, the mega electron volt microscope, the size was mainly the acceleration region, that you start emitting electrons and then you have a series of capacitors to speed up the electrons to the acceleration voltage that you want to have. So, and if you want to get 1 mega electron volt, you need to have a very long acceleration tube. Today,
Okay.
we're working this range of 300 kV maximum. This is what you get from everyone working the field. So that size is under control. So the main difference in size now, if you want to add one of those correctors for your objective lens, you're going to get extra 40 centimeters approximately. If you want to add one of those correctors for your condenser lens, if you want to correct your stent probe, you get extra 40 centimeters. And then if you want to put one spectrometer below everything else, you're going to grow a bit more. So it depends on the elements that you want to put there in addition to the basic optics.
Okay, thank you.
So then here is where TM is today. This is the most advanced that is nowadays. It's a system in Germany, and there is one in the US that they can get information transfer better than 50 picometers. And this is an image that I took on that system during my postdoc there in Jülich. And this is the reconstruction of the wave function to analyze local potentials. And basically, that's a bit of how to process the image and how to investigate the sample. What we're able to do directly now is to correlate with the structure. And back then, I was trying to get information on the oxygen vacancy localization on the catalysts. So this is a bit on the mindset on TM imaging. But then now I'm going to shift a bit to a different topic, because this is TM, and it got a bit stuck with that back in 2014 and 15. And STEM started to get more fashionable. And STEM, before the correctors, was not very interesting. Resolution there would be, well, let's put it into 0.15 nanometers, 0.14 nanometers. So it could not get nice atomic resolution for many materials. So TM would get these atomic lattices, and STEM without a corrector would be more limited. And the main reason is that, let's just think here, what we want to do in STEM, scanning TM. You want to make the smallest probe possible, because then locally you can form the image and you can get spectroscopy signal. And to make a small probe, you need to demagnify your source. So you have your emitting gun, and you're going to have the first crossover, and you want to demagnify it at top of the surface. And then there's a question of how bright is the source, so how many electrons you can demagnify to make a electron probe, and also a diffraction limit story. So basically, when you try to make a very small probe, you come across the diffraction limit. And this is, you get from Abbe's equation. So the diffraction, the minimum size that you're going to get is related to the wavelength and basically your convergence angle. So that means that if you want to get sub-angstrom STEM probe, if you want to get better than 0.1 nanometer, you need to make a convergent beam. And this goes, well, it's a very simple calculation. And then the price that you pay when you try to open your convergence angle is that you're going to work with more scattering components there coming from wide angles. So you have more influence of the aberrations. So it's the same idea of the aberrations that I mentioned before on the objective lens is exactly the same that you have on the condensing system. So, and then these aberrations, they start to get more aggressive as you get more convergent. So then in practice, when you're in STEM mode, you're using the microscope in a diffraction mode because you want to collect different scattering ranges, very large scattering ranges for high angular dark field. If you want to have Z contrast, you are going to collect intermediary angles for diffraction contrast or small angles for bright field. But then if you want to make a very small probe, you need to get convergence, and the convergence is going to reflect on the probe size. You can make a smaller probe size, but then the diffraction pattern is not going to be in the point-like. So one reflection is not going to be a simple sharp peak or a sharp line as you see on the diffraction pattern, but it's going to be a spot. So then this is what you get in practice. Then what you have when you're doing STEM, you're typically working with a higher convergence angle. And then here in practice, how we see it, and if you want to play with this concept, there is one free software from Forschungs- and Jülich that's called Dr. Probe Lite, that you can do simulations and just understand a bit more of the optics. And the idea is, if you have a 300 kV electrons, and you check here how is going to be the central spot of your diffraction pattern with a high convergence, 50 milliradian, and a spherical aberration of 1 millimeter that is typical for an uncorrected system before the advent of the hardware correctors. Only a certain part here is going to give you a nice transfer function, because you start to get aberration, confusion outside this region. So that means that here, only this part would be a good optical component for your beam, and this would lead to a limit in the convergence angle and a limit in the probe size. So here's a simulated probe size that's about 1 nanometer. And the question is, after we introduce the correctors, what happened is that it's possible to clean up the Hontigram much more. So this means here that up to 72 milliradians, there is no confusion on the transfer function by the condenser lens. So that means that the aberrations are not limiting the imaging aspect there. So just to put in a simpler way, when you're thinking about STEM, you want to make a very small probe. To make a very small probe, you need to be convergent. So you beat the diffraction limit. But then as you start to get convergent, you have aberrations. And then only with the aberration correctors, we start to get nice images coming out of STEM. So then here are STEM images with atomic resolution, and here's much safer. You're probing point by point, and you got signal point by point. So when you see an atom, you see an atom. There's no no way to get wrong it here in terms of high angle scattering. So here's one example showing what we can get today when you're looking at the gallium nitride sample, for instance, and when you do the full heat transform and see the frequencies we're transferring, we're below this 50 picometers level. And here, for beam sensitive samples or to explore different scattering mechanism, we can go to lower kV and we can get a sub-angstrom even at 30 kV. So the resolution improved quite a lot. And here in this slide is to give a flavor on where is it today. And well, this is where we are in terms of resolution. And I'm not going to comment much on it. I just want to share where the TM can get in terms of resolution today with the correctors. And of course, if we make a small probe, you can do chemical mapping locally. So here's a chemical map with atomic resolution. You can tell the different atomic columns easily here, the dysprosium and scandium columns. And here you see the spacing between those two green atoms that we have on the light profile. It's 76 picometers. So this resolution can be also used for mapping chemistry with very high resolution. But more traditionally, we don't go to this kind of maps. Most of the times, we have a bunch of nanoparticles or a segregation of different materials in layers. And what we want to do is to have chemical mapping localized for the different particles. But then this is just to give one idea of what you can do today with the TM. And here, the question is that it's possible to do this in a quite fast way. One chemical mapping like this, it's something that takes about 1 minute. So it's much faster because of how we can shape the probe finely and how the detector technology evolved. So here I just want to make a break point to check how we are with time, and if I have a bit more time to comment on some more practical aspects, or if you want to make questions on practical and we just discuss on the possibilities.
And I think we can take questions at this point before you go on the more practical aspects.
Mm-hmm.
I mean, just quickly, in half an hour, it will be midday, it will be noon, which is usually a time where people start to have another focus. So you still have half an hour. Please, Andre.
Yeah, so Daniel,
Sure.
Go ahead, sorry.
No, I just want to check, because this is a breaking point. I have more slides to share some of the ideas on how to form images and how to play clever with the detectors. But it would be also a good time to just get your questions and discuss your ideas with the app. So whatever you'd prefer.
So I have a very basic question.
Sure.
In this last slide that you've shown the chemical mapping, so can you do, so you said that you can acquire images really quickly. So can you do real-time videos, for instance, for chemical reactions? Can you see how hard would it be if it's not it's not possible to see that?
So chemical reactions, they are very fast. They are outside the time range. So here, just to give you a typical timeline, a TM image, when you do one shot, one projection, typical duration of one image is 1 second. The fastest we can go would be 1 millisecond. So we can get down to 1 millisecond. Then STEM, a typical map image. So a typical image takes about 20 seconds. A chemical map will take a minute or so.
Okay, that's a lifetime. Yeah.
Chemical reactions, there is another way that you can do, but it's something that I was not I did not have in mind to discuss, is that you can use laser excitation of the tip and laser excitation of the sample and do the illumination in stroboscopic mode. So then you can do time delay exciting the sample. So if you have a reversible process on your sample, you can study down to, I think that you can get faster than nanosecond resolution, but then in a stop motion way.
Okay.
But this is quite far from the traditional.
Sir, you mentioned before you can get from 10 images also oxygen vacancy. I want to know how it is looking like, the oxygen vacancy by using 10.
Well, quite difficult, I would say. So there are many ways that you can explore seeing vacancies or seeing different effects. And if you think in terms of scattering, what are the ways that you can try to see them? So one way would try to see chemical events and counting, but this is not very efficient because you're going to have an error in the counting that is too large. What I try to do is to reconstruct from a series of images to reconstruct the wave function. And then if you're missing atoms there, you're going to have less of the phase shift as the wave goes through. And then I was trying to analyze this effect in the image. There are other ways to do this with holography, so that you have interference effects to try to measure. But then so far, and this is where I stopped my research area. So, and I've been following because this is what I was researching. So far, it's not possible to count single atoms with this approach. So if I want to count number of vacancies, still there will be a noise in the phase that you can define, that you can retrieve experimentally, that you cannot count single vacancies. This is as far as I know today. But then there are some approaches that you can count atoms, tomography reconstruction methods, or intensity analysis on images. So there are some interesting ways that you can count and reconstruct 3D shapes with atomic resolution, but the direct visualization of single vacancies is not realized at this moment.
Thank you, sir.
At least as far as I know. Maybe as we speak, someone is making it happen. Good. Shall I share
I have a question.
Sure.
Yes, I have a question about because here you talk about SEM, TEM, and STEM, right? 3 different measurements, I think.
Actually, I've been talking only about transmission. So transmission in traditional way, that's TEM, and traditional in scanning mode, that is STEM, STEM. SEM, it's quite similar, but then you don't go with the signal that goes through the sample. So typically use bulkier samples.
Okay, and I wanted to know that with both STM and TEM, we can get the crystal structure, both crystal structure and also the chemical composition, right?
Well, yes, but then the STEM mode, the TN mode, and the diffraction, they are done in the same microscope. It's the same equipment that can do all of those. Oh, okay. It's actually a click of a button to change the optics and to go in between the modes. So if you want to do chemical analysis, well, nowadays you want to do this localized, so you want to do a chemical mapping. In the past, the detectors were not so efficient. So typically you would illuminate a large area and count the X-rays from many particles, and you have an average of the sampling. But then the technology evolved, and now it's possible to have this localized information down to the atomic column. But it's the same microscope that you can just switch modes and to go to that high resolution TM that I showed, that's the interference image, or to the diffraction mode that you get the crystalline structure.
Then, for instance, if we have one of STM or TM, we don't need like XRF to select the characterize the chemical composition, right? Is it correct?
Not exactly. So the techniques, they'll have complementary aspects. So when you go to X-ray based techniques, you're talking about a different interaction. So typically you can go through thicker samples. You have a different behavior of multiple scattering. So typically you get much better energy resolution. So if you want to do fine structure analysis, a synchrotron, there's no way to beat it with a TM. But then X-rays are very difficult to focus. So you cannot go and measure a single atomic column or a single particle. So typical typically you use those techniques side by side. So if you want to have a global overview of your sample, and then the spectroscopy techniques and X-ray techniques are going to be very good. But if you want to go down to a single particle or to a small region in your device, then TM gets much more attractive.
And at the moment, from the devices are using in different companies, and different companies are producing them. For instance, for defining the size, for characterizing the size of material in nanometer size, STEM is more exact, or TEM is more exact, or both?
I think that what I see in the projects that I discussed is a bit of a combination. So if you want to count particle size, for instance, if you are working with catalysts or metals and you want to see grain boundaries, TM is faster to use and it's going to give you a good overview. But sometimes you're going to have some artifacts on the imaging due to diffraction. There are some grains that are going to light up because they are diffracting heavily. So there are grains that are going to be bright and other dark, and they are going to be the same material. Then the STEM is a bit slower, but then you can get a better feeling on the composition of the material. So it depends on what you want to learn and how fast you need to go. So if you want to just see particle size and you want a good approximation, a fast process, TM is the easiest one. But if you want to be more precise, STEM is going to give you a bit more precision there.
Mm-hmm. Thank
because
you.
there's less delocalization, for instance.
Mm-hmm.
Good. Any other question at the moment, or may I share something just? Oh,
I have a small question. Why we are, when we start to use TM, the technical is asking this material is magnetic material, or
that's a good one. Yeah, there are two reasons. One very practical, and the other is just on the what you expect to get. So imagine that you're going to put a magnetic sample inside a microscope, and it's just inside the objective lens. And at 300 keV and regular excitation, you can get fields on the range of 1 to 2 Tesla. Imagine that you have a magnetic sample there, and you want to move or tilt.
okay.
So, yeah, the sample may just come out of the sample holder and attach your objective lens. So then you have a problem. And then this is a very practical problem. So if you have magnetic samples, you need to think on how to attach. I have one slide on this later on the presentation. But then one less dramatic effect is that imagine that you have a sample that behaves like another lens. It's going to deviate the electrons. So you're going to have extra astigmatism. It's going to be a bit more challenging to focus the image and to get a high quality. It's going to be somewhat limited.
Okay. Thank you, sir.
No worries.
Okay, I think you can proceed.
Yeah, so the next part, it's about on how to play smart and get informational samples. And actually, the question on magnetism is an interesting one because it's somewhat related. So the idea is that, okay, the fundamentals on how we image and how we work with the microscope are there. I think that you got some idea on that. But then the challenge is how you get to the most difficult samples or the most practical problems that you want to answer. So then here, first you need to fit the sample to the TM. There are many techniques. So if you have a material in a suspended solution, you can just drop the solvent over the grid. So this is a typical grid that we use for TM. It's a 3 millimeter copper grid that is covered with a thin carbon film. If you have a bulk material, you can cut part of it. You can do this as a mechanical process, or now there are SEM tools with a dual beam that you can just cut a small piece and thin it down. So this is a FIB lamella. But essentially you need to get thin enough so the electrons can go through. And you need also to keep in mind that there will be always effects. When you prepare the sample, you may be damaging something that you want to see, and you always need to take into account for the different preparation methods, what's the solvent going to do to your sample, if the sample is going to see any high temperature in the process of preparation, or if you're going to implant ions or do surface damage. Those are practical things that you need to keep in mind for the preparation. Then there's a question of, you're going to put inside the TM. And TM, you have a high vacuum level. And you can imagine that the sample is going to suffer. So here, imagine that you're packing your sample, well, inside a low pressure environment. And there are some ways to go around. Basically, you can keep the sample in a liquid environment or even a gas environment. Those are called in situ experiments. I mentioned this before in very low level of detail. But there are ways that you can put liquid inside the TM, but it's just a thin layer of liquid because electron needs to go through there. So there are some possibilities to go around, but you need to think that the standard TM, the sample is going to be in vacuum. And some samples can cope well with that, some samples not that much. Then the magnetic fields, as I was just discussing, if you put a magnetic sample, even a small piece of magnetic sample, here in this carbon film, it used to be a lamella. So what happens is that when you put it inside of the microscope and start the process, you generate force. If you try to move a magnetic sample within a magnetic field, you're going to have Lorentz force just pulling this out. So essentially, you can lose your sample, or you can damage the microscope in a way. Imagine you have an extra magnetic component attached to your corrector or to your lens. So this may be a big misalignment question for the next user. And the most important is, well, your sample is going to receive a lot of electrons. So the electrons are going to travel through the sample and they're going to interact. So here's a Monte Carlo simulation for elastic scattering, for you to have an idea that depending on the material and on the thickness, the electrons are going to go crazy and they're going to interact with the regions of the sample. And this is going to depend on the atomic types that you have there. And also the interactions, they have different scattering cross sections. So the probability of a certain scattering event to happen is different. The idea is, well, the electrons, they go through the sample, the electrons like to interact, the sample is going to suffer. In practice, what you see are some effects like radiolysis. Radiolysis is basically you're breaking bonds. It's most common in organic materials that you're breaking carbon to carbon bonds and you're changing the structure of the material. You have knock-on atoms that is more common for light elements. So if you take a 300 keV electron and shoots against the sample, you may have a collision that's enough to take out the light atom out of your sample. You generate heat. Charging is not so common for TM because of the cross-section. You use thin samples, but for SEM, it's a nightmare. So you need to take into account that your sample is going to see electrons. And if these electrons are damaging your sample or messing up your analysis, this is something that you need to think before you go to the TM to avoid disappointment later on. And then the way of thinking an experiment, then it's my approach to you. Think what you want to know about your sample and how you can relate this to scattering on the TM. And then you think if you have resolution enough to solve that. And that was the way that I started with microscopy. My first process, I was trying to look into dopant segregation by checking the shape of particles. And then this shape, if you are in thermodynamic equilibrium, it's going to follow a certain Wolff rule that you can calculate ab initio the surface energies and estimate the shape. So when I started microscopy, I was trying to correlate chemical composition from the shape of the particles. Then I went on with the oxygen vacancy story and tried to identify dopants, and then I was using spectroscopy. So there are so many problems in real material science and in physics that you can address with transmission electron microscopy. That's, well, I could keep talking here for a long time and will not cover the surface there. And besides this first layer, it's important that you think on how to optimize the experiment. So even if the experiment is possible, there are easier and more difficult ways to get the same information. So depending on the high tension that you're going to have, you may have more signal or less signal, more damage or less damage. Depending on the detectors you have to collect the electrons or X-rays, you may have a better time understanding the physical feature you're looking at. But then the rule of thumb here is try to use as few electrons as possible, because the more electrons you put, the more damage you do to the sample, the more you change the sample along the way. And with this, in the recent years, there was a push to play smarter with the detectors to work at a lower dose. And this is the last part of the talk here. I may need to cut it shorter because of the time. If you have interest, then I can go more in detail. It's just on a concept on how to use a segmented detector to get smarter with your detection, to be able to see more and see with less dose. So the idea here is that there is a traditional technique that is called DPC that uses a segment detector to locate where the electrons are landing. So when you're in stand mode, you can capture electrons that are deflecting more or less. And traditionally, this was used with magnetic materials. So if you have here hexaferrite material, what you have is that depending on where you're parking your beam, depending on the region you're parking, you're going to have a deflection of the electrons, a global deflection of all electrons going through the sample. And then basically, if you use the segments and subtract the opposite regions, you can have a vector. And if you do this point by point, you have a vector field mapping the deflections your electrons feel when going through the sample. And with this, you can map the Lorentz force effect that the electrons feel when going there. And you can map this in a color code, and this generates a visualization of the magnetic domains in the sample. The question is, you can measure this as small as you want. As long as you can make a small probe, the electrons are going to deflect just the same. And this gave rise to the new technique that I want to mention you that's somewhat new, that's called IDPC. But then DPC, just the differential phase contrast, gives you information on electrostatic fields and magnetic fields that are going to deflect the electrons. So this is a way to use a detector to be clever and to capture magnetic information, for instance. Here, I'm going to skip this part. It's about how the electrons deflect and how we think in terms of center of mass for a bunch of electrons going through the sample with a convergent angle. I'm going to skip here because those are more physics details. But then the basic idea is that when the electrons go through the sample, they are going to feel the potential of the sample. So if there's a magnetic field, if there's electrostatic field, or even the core potentials are going to be felt by electrons, and they're going to deflect. And what we can do is that if we measure these deflections, we can have a sensitivity to know what is the potential that our electrons are feeling when going through the sample. And then it's a much small effect than a big deflection of the diffraction pattern, but then it can be measured. So here is just a simulation indicating that this can be detected. So basically, when you travel next to a single gold atom, if you travel just on top of it, you have a distribution of your intensity on the diffraction pattern. And when you go next to it, so if you step the electron being a bit to the side of the atom, you have just a distribution that is slightly different. And this is basically the electrons are feeling and getting closer to the potential. And in practice, what you do is that you just adjust the optics to have this landing on your detector, and you enable the individual segments. So then each one of the segments, pixel by pixel, is read out separately, and there's a subtraction of the opposite segments, so you have a vector. And then there is a vector field integration. And here, the physical idea behind is that the deflection that you have, this center of mass that is changing as you travel through the sample, is related to the electrical fields on the sample. And then if you integrate this contribution, the integral of the electrical field gets you to the potential. So that's the idea of mapping potentials in the sample using a segment detector. So that's the idea of the IDPC, that's the integrated DPC. How does it look like? Is that you get information on the heavy and the light elements all together. And here, if you think traditional STEM gives you an image like this, that's quite nice, quite high resolution. It's the same material I put here to comparison, but just I had to magnify a bit to match it. But then here you see that traditional STEM imaging with high angular direct field is blind to light elements. And if you want to see those light elements, you need to have a scattering range that gives you more contrast for potential. So here, the high angular dark field, the signal is proportional to Z square. So it's Rutherford scattering, and IDPC is proportional to the potential only. And then just to finish, this clever use of the detectors allows us now to see even hydrogen atomic columns. So we can see hydrogen atoms in the TM using this because of this contrast that we played smarter with the detectors and allow us to see very beam sensitive samples that can only survive a very small dose, a very small amount of electrons. And then this is just one example that I want to share with you, that just thinking is smart in terms of what are the electrons you have there, what is the physics that is happening with the sample. So if you optimize your collection, if you think what are the electrons that are going to give me contrast to see what I want to see, you can get to new science. And to me, that's a pretty nice thing, that instrumentation is hand in hand with new science. So then, just on the interest of time, I'm going to stop here. I'm going to...
Excuse me, sir, the internet is not stable. It is shut down each 2 minutes.
Sure, yeah. So here, I'm thanking you for your attention, thanking the Department of Physics and my mentors there, Claudio, Chiquito, Edson from the chemistry department, and my colleagues, well, at the university. And I'll be happy to take questions now, or if we don't have time, I leave you my email here, daniel.stroppa@thermofisher.com. If you want to discuss further, because we're running out of time here, I'll be happy to take your questions and try to help you think in terms of what is possible with the TM today. Thank you.
Thank you very much, sir.
Thank you very much, Daniel. It was very nice. Mahmoud, you wanted to ask?
No, sir. Really, I miss many slides because the internet. Yes.
Okay. So as usual, I will put on YouTube on the webpage of the program the presentation if you want to go back to it.
Okay, sir. Thank you. If it is better if he share the presentation with us. I hope.
I just have a maybe non-scientific question. I just wanted to know the medium price, the typical price for STEM or TEM.
Well, I am not too close to the commercial side of the story, but I know some numbers. For an uncorrected system, you will be looking at something that can go, well, let's put a ballpark figure here, that will be around 1 million euros. So this without a corrector. When you add the corrector, well, typically, it's not only the corrector that's coming. People, when you're designing your experiments, if you want to put a corrector to get extra resolution, you're typically going for more expensive detectors, you're going for more advanced holders, and, well, there's a lot of things that you start to add up. So the more complete configurations, they typically land in the range on the 3 to 4 million euros. But then this is just a ballpark figure, because there are some accessories that are more expensive. There are ways to get simpler. But just to give you an idea on the approximate range there.
Okay, thank you.
Okay, so it's typically a shared, for lab research, it's a shared infrastructure between different groups or a department.
Yes, the most common is to have this in a multi-user facility that people from different departments can use and share the expenses, because it's a complex infrastructure in the end.
So Daniel, just a quick question regarding when you were showing the slices, you said that you have to select the slices very neatly so you can have less than a 2 pi change in the phase of the electrons, right? So what you just presented, now this new technique is correcting that, right? In a way.
No, actually, that multi-slice story it's just a way that I find easier to present, so you understand how the electrons are feeling the effect of the sample. So if you think that you have electron wave propagating slice by slice the sample, the way that we calculate and simulate images, but then, well, the physics or the realities that your shining electrons are going through and you're capturing.
Oh, I see. I see you have a parameter that you have to select the information to give to the microscope to say, oh, look, the phase here is shifting by some amount. So, oh, okay.
That's
so
a way
just
to try to understand the image formation. So what you get in the end is that you set up the before the sample and you capture what's after. That's
okay. I see.